Yeah, so the idea was to have two parts of the tutorial. So the first one was to look into the really the kind of library underlying all of our computations, which is called the Liva library. And the second part was to actually train a neural network to do something. I think we'll just stick to the first part because yeah, we're short on time. But you still have the second tutorial on training the neural network to do classification on some video data, basically. So yeah, you can still play around with it after. So there is one layer of complexity that comes with having this neuromorphic hardware. So we are trying to interface between build an interface between CPU and GPUs and neuromorphic chip, and you really need tight integration between the computation you want to do and the hardware itself, right? Because these gains that you have in time and energy requirements are in the end coming from the constraints that you have on the hardware itself. So you need to tailor the application to the hardware. And to do that, we have this Lava library that kind of abstract the programming paradigm away from the hardware a little bit and try to hide some of the implementation details that are not always useful, or try to speed up the development of new applications. So you can use Lava at different levels. The more general, like application-oriented one are these application-specific libraries built on top of Lava. So we have Lava optimization, which also contains the Kubo solver that Philip mentioned. Then we have Lava deep learning, which implement the training of spiky neural networks using Torch. And then there are also other libraries like Lava peripherals, for example, to connect the chip to different I/O devices and sensors, or Lava VSA that goes into hyperdimensional computing. So yeah, behind all these libraries, then there is the Lava library itself, which kind of provides the interface to the chip and to the abstraction mechanism that we use. We'll look into this concept of processes and process models. And you can still, like the Lava library provides different processes that you can combine to build your own application, right? So different neural models, for example, or different algorithmic components that you can then connect together to build a new application. And then, of course, you can also implement your own processes and process models, and yeah, also interface the library with new and different hardware backends. So this is the kind of structure that we have. We have different layers. We have the application library on top, Lava library, and then then we have the compiler, which takes care of taking your abstract specification of the application and then translating that to the specific hardware backend that you're trying to use. And then there is the runtime, that is the specific code that runs on the hardware platform that actually execute your application. So we start with this concept of process, which is the abstract description of an algorithmic component, right? So if we go to the Kubo example that we had before, for example, the process could be the variable itself. So each neuron that represents a variable can be a process. And then there is the another process are the connection between the different neurons, right? So the process is kind of the atomic component of an application. And this is very general, so it can be like a connection, synapses, or it can also be an interface to a sensor that then streams some information into the chip. So we start with the process description. Here, for example, we have the LIF, that is the leaky integrated fire neuron. Here we have the documentation. So the process describes the input that you can give to this algorithmic component, the output, and also the internal memory, which are called variables, which is what is stored then in the on-chip memory. So we can take this link integrated fire neuron that is already implemented in Lava, and we can instantiate different populations of neurons, and we can then connect them. And this is what we do in this tutorial. So we start with we instantiate the first left neuron here. We specify the different characteristics, so the threshold, the kind of which in the end parameterize the dynamics of the neuron. Then we can also instantiate a dense layer, which is somewhat like a linear layers we have in deep learning libraries, which can connect to different neuron populations together, and there's some weights. And then we instantiate a second leaf component, right? And then we have this, here we show like what I was saying before. So a process is really a collection of the API of a particular component. So we have the input ports, we have the variables, and the outputs. And in the case of the leaf neurons, for example, we have this imports that allows the neuron to receive incoming spikes. And then we have some internal state of the neuron, because as we said, we have stateful neurons. And then we have output ports. So they basically transmit to the other neurons the outgoing spikes from the leaf. So we can actually inspect the interface given the instantiation of a specific process. We can look into the port that we have, such that we can understand how we can connect it to different components. And for example, in the leaf process, we have an import that is called A-in, like a shortcut for hexon in from the neuroscience terminology. And then we have S-out, which is spike out, which is from the port which is sending the spikes to the other neurons. Right, and using these ports, we can connect together the two leaf components. So we just type the process we want to connect dot the port, and then we can connect to the import of the next layer, right? So we have the leaf, we have the dense connection, which are the synaptic connections, and then we have the other population of neurons. It's like the interface that you have to connect in. Right, and in the same way, in a similar way, we can also inspect the internal state, internal memory of the process, which are the variables, which have a specific shape, which is constant. So when you describe a specific, you instantiate a process, you also specify the shape, and then you also have the type, of course, like the precision, which changes usually based on the platform, right? So if you're running the process on CPU, you can have usually higher precision, but then if you move the some specific component to the hardware, you usually have lower precision. Right, and we can visualize all these internal variables. For example, in the dense connection layer, we have the weights, of course, so we can just type the process dot the name of the variables dot get to see the initialization of the variables here, in the beginning. Right, so Lava also provides these utility functions to track the state of specific variables, or also like the spikes through time. With this component that is called a monitor, you basically attach a monitor to a specific variable such that you can record the activity through time, and then you can inspect and visualize it. And this is what we are doing here, such that we can track the state of the leaf neurons. Then to specify the execution, you need to specify like a run condition, which is basically like a stopping condition. So you can either run continuous, so let the network run until it finishes in some way, or you can specify a number of steps. And then there is the second part, that is the run configuration. As I said, we have a kind of multi-backend environment, so we can either run on CPU, on GPUs, on the LOE chip, and you can specify this in the run configuration. So based on the kind of hardware that you have at hand. Usually you start developing on CPU, that's what most of us have access to, but then you can also port the application to the LOE, and then you can change the run configuration to actually ask the runtime to be run on the chip. Yeah, so we specify one of the processes we want to run. When you have multiple processes connected together, you just need to run one of them to activate the whole network. This is what we do now, and we have the lift2.run, and then we just pass the run condition and run configuration, and this will run for a number of steps. Then we can use the monitors to get the reported data that will just basically like track the activity of the network through time, and we can visualize this data. So in particular, what we have here is the voltage and the current of the network, and of the two components. So each color of the in the graph is a different neuron because each of this population have several neurons, right? So on the left, we have the first population, on the right, we have the second population, and different colors have different neurons. Then after we actually execute it, so that the network remains idle in the background, and you can either like run it again without like recompiling it, or you can also stop the network. And this is what we do here, right? So we stop the network. So this is the interface that you have if you just want to combine different components that are already implemented in Lava. There's a question there? Yeah.
Sorry, maybe it's a stupid question. What are you running? So where's the input specified? What is the input here?
Yeah, so in this case, it's there is no specific input to the network, but it's the dynamic of the network is driven by the neurons themselves. So there is some noise in the neurons accumulate voltage through time, and then when they reach a particular threshold, they will send a spike. So
what do they know?
Sorry?
This is a simulation of how the chip would work, right?
Yeah.
So if I do nothing, then the chip creates this kind of pattern?
Yeah, so it really depends on the specific neural model that you're using. In this case of the link integrated fire, you can have a bias term, and the bias term is basically so you can understand it as a sort of recurrent connection in the neuron. So the neuron will increase its activity through time until it reaches a particular threshold, and then will spike, right? But this is just a specific example, like because of the neural model that we have. But of course, yeah, you can have input from either a device, or you can also feed images or a stream of data to the network itself.
I'm just wondering whether it's not a problem that there's so much activity without any kind of operation being executed or demanded by the user. This is just idle state, right?
Yeah. I mean, this is specified by the when we instantiate the leaf components. This is something we are specifying there. I can show you. So if I go back here, we have this bias term here, which it is basically like explains this activity that we have in the network. In the second one, you see we have a bias in terms of 0, and if you actually go to the tracking of the network, you see on the right that there is the population of 0 bias. It's not spiking from the beginning, but it's kind of only spiking when you receive spikes from the first one. So you can understand like the lift one is driving the execution, so it's actually emitting spikes spontaneously. These spikes are transmitted to the lift 2, and this actually like accumulates spikes over time. You see that this is increasing here, and then when it reaches the threshold, then you also have spikes on the second component.
Maybe I can add something. It might become more obvious why it's useful to look at specific applications. You might remember this Cubo example for the optimization that I just mentioned. This would be one example where you don't have any input, and the whole everything that you are interested in comes from what the neurons just do iteratively in this dynamic system. That means you create this recurrent network in a way that the lowest energy state of this network, or one of the stable attractors of this network, is actually a solution of the Cubo problem. And all you do then is basically just, you don't provide any further input once you have set up the network, you just let it iteratively run without any input, and only at the very end, the network will give you an output that is equivalent to one solution to the Cubo problem. Or another application would be a simulation of dynamic system, like weather dynamics, where you say you just encode the simulation into the chip without any input that needs to be provided, and then you just let it run for a long time. So the chip simulates the dynamics and only provides some output later on. Those would be examples where you wouldn't need an application, where you would need an input. And this is one application showing you how to run such a network just without input. I hope that clarifies things.
Would it not possible to do it with an input? So I would imagine that I would want a network where I provide an input and it solves a problem that's specified by the input, instead of having to recreate a new network every time I have a different instantiation of the problem.
Sure.
I think he will actually go into the MNIST.
Yeah, so I mean, we'll not have time to go into the second tutorial, but of course you can have, I can like do a little bit of a teaser here. So you have of course, you can have input in the network, and what I was showing is just to explain the interface, but you can also have networks that are like idle. If you have no input, then the input is fed based on the problem that you're trying to solve, right? So the other example we have in the repo is this NIST classification task, where the input is this video streams that are generated through, let's say, saccadic movement of the eyes, looking at a particular digit, right? So this is the input of the network in that case, and then you have all kind of spikes through the network, and in the end you get a classification of the digits, right? So yeah, you can have both cases. In some application, the input itself, it's not a signal that you fed into the network, but it's the structure of the network itself.
Yeah, it's just unusual, right? So when you solve the cubo problem, I mean, my expectation would be I put in Q and I get the lowest X, right?
Yeah.
The X that solves it. But you would actually, given a Q, you create a new network.
Yeah.
And then you let the network work for some time without any input, and then the solution, this will give a solution, right?
Yeah, exactly.
It's a fundamentally different kind of approach.
Yeah, exactly. Yeah, it's different from the kind of deep learning computation that you can have in that case. So the input of the network, the input is basically generating the network, right? So you have the Q matrix of the Kuba problem that used to create the weights connection between the different variables, and that encodes the problem. You have this network that encodes the problem. You just let the network run, as you said, to get the solution.
All right. Thank you.
Yep. Any questions? Okay, so we can proceed. And the next thing I want to show is how you can create custom processes. So you can either combine existing processes together to like build a network, but you can also code specific components, specific processes to encode the different behavior. So we start with, we want to create this spike generator. So this is something that can be understood as a input, basically. So it's in some way we are also answering the question. So we can have an additional process that is generating an input for our network, and we want to just say, yeah, we can specify a spike probability, and at each time step we'll have this process, this spike generator, that will create spikes with some probability that the user can specify. So we start by creating this process, spike generator, that inherits from the abstract process that we have in Lava. And then we just need to specify the constructor, where we specify the variables, so the internal state of the internal memory of the process, which in this case is the probability, the spike probability. And then we have the output, that is the ports we will use to send the spikes to the actual network. So yeah, the process somehow like describes the abstract interface of the component, but then you also need to specify the behavior, right? And the behavior, it's tightly coupled with the hardware you're running on. So we can have different backends for Lava. We can have, of course, Python. We can have C or C++ in some way, and then you also have assembly code if you want to run on the Neuromorphic chip itself. This specification of the behavior is done through the process model, which is basically describing the specific implementation given a process. So we can go ahead and import some stuff. And what we have here is the process model of the spike generator. So what we do, we start with we implement the PyPloE process model, which is this kind of protocol of executing the network, where you have a phase where you're spiking, you're generating the spikes, which is then implemented in this run spike function. We create the actual, we have the abstract specification of the variables and the outputs. Now we create the implementation of that, and that's what we have here. So the spike probability, which is an integer, and then we have the S out, which is the output, which is actually we have the implementation. Yeah. Then we can go ahead and specify the behavior in this run spike function, will be executed each time step. And we just use NumPy in this case, since we're running on the CPU, we can just use Python code. We generate the spikes in some probability, selecting between 0 or 1 based on the probability that the user provided. And then we send, we have self.sout, which is the output, and we send these spikes through the output. This is something that is entirely like user provided in a way. So if you want to create a new component, you just need to create a process which describes the interface and then a process model, and then there you can actually implement the behavior that you want. Right, so we can recreate a similar kind of scenarios that we have had before. We can instantiate two populations of leaf neurons. In this case, you can see that we have a bias term that is 0 in both cases. So if we actually just connect these two leaf together and we let the network run, we will see like a flat lines because there is no kind of driving inside these neurons. But then we can also connect the spike. So we do the usual stuff as we did before. So we instantiate the network, we connect the two population together through a dense layer. But then we can also instantiate our spike generator that we just created. We instantiated the process here. We specify the shape and the spike probability, which is more spike percentage. Then we instantiate a second dense connection. And we use this dense connection to connect the spike generator to the input port of the leaf one, right? So in this case, the input itself is generated by the spike generator. As usual, we connect everything together and we run. And what we see here is basically the behavior of the network, which is similar to what we saw before. The difference is, as you can see in the first plot on the left, you don't have like a regular pattern there because it's not the network that is driving its own activity, but you have some random spikes that are incoming to this first layer of leaf neurons. This is causing the voltages to be updated, and when they reach a certain threshold, they will spike and send the spikes to the second layer that will then do the same. Okay, and then we can stop the network, and this is kind of the end of the first part of the tutorial. Will likely be the only one. I will go quickly on the second one if we don't have questions. Yeah.
Sorry, I came arrived a little bit late.
Yeah, no worries.
Obviously, these walls are different than normal rates. And the second question is the generator. Is it an immediate thing that happens or is it with a delay? Because I understand that bits of an image turns into walls with the generator.
Into what?
It converts these inputs of bits into walls, right? The generator. Yeah, so also the drug. Like something just happens immediately, or does it take time?
No, it's like there are two cases. So in this spike generator here, it's something that happens immediately in the sense that you have a concept of time step, right? So you, in the end, the spike neural networks can be understood as a discrete time dynamical system, right? So at each time step, you can the spike generator generates spikes randomly, right? Based on this some probability that you can pass to the spike generator. But the distribution itself, it's really up to you, right? So you can do whatever you want there. In this case, we have like binary spikes, so you don't really have much choice. You just need to specify like probability to either spike or not spike. And this will be executed at each time step. And in the next time step, the next layer will receive the spike right through the these connections that you have. Does this answer your question? There was a second question.
I misunderstood something. No,
okay. Anyone else? Okay, so this was an overview of how you can create like custom components. But I will also quickly show you how we can actually build on top of that and like develop more complex application. Yeah, specifically what we can show here is this classification task on the NIST dataset, which is a neuromorphic variation of the well-known NIST dataset. Where you start with the classical digits, you transform them into this sequential like video input somehow based on the saccadic movement of the eye. this is like an artificial data set, but of course you can understand that this is something you can have something similar coming from a sensor, for example, like a neuromorphic camera or something similar to that. And then what we want to do in this case, of course, is classify the image. Right, so yeah, we import some stuff. We import the data set. So all of this, as I said, is built on top of PyTorch. So you can use the usual like data loader data set as you had in Torch. So we can instantiate our network, which in this case is composed by 3 layers of these Kuba components. There are somehow similar to the Lift components that I was showing before. And then we have dense connection between the different components. This is like just a module list as we have usually in Torch. And even here we have the weights are like initialized randomly, but then we want to train them. And we use this mechanism that Philip showed before. So we have from one side, we have this credit assignment through time to do to implement the backpropagation, but then we also have the surrogate gradient to smoothen out the spike function such that it is differentiable. So we implement the network with the usual kind of setup, implement the forward function to specify the behavior of the network in the forward pass, and then Torch, of course, will take care of the backward pass. Then we can move the network to the device, in this case to the GPU. We can instantiate the optimizer, which we are using Adam in this case, and then download the data set and create a data loader. So you also have like batch size, all the usual stuff that you have in deep learning. We can have another look at the input data. Then the next step is specifying the error function. So in this case, we, as you said, we have an input stream that is through time, right? So we don't have really a kind of a target output for the network, but what we can use is the frequency of spikes to classify the image. So we'll have an output layer which has the same size of the number of classes that we want to specify, we want to classify. And then what we use to classify is the spike frequency. So we want to maximize the spike frequency for the neurons, which is associated to the class, to the true class in the dataset. Yep.
Does that mean you lose kind of time to solution with an increasing number of classes?
What do you mean by
time to encode it within single ticks, so to say, your classes? You have 10 classes, it takes not as much time. If you have, let's say, 1,000 classes.
Yeah, so these are kind of, it's the shape of the output layer, but these are like in parallel, right? So you're not like increasing the depth of the network with the number of classes, but you're just increasing the width. Yeah, I mean, so what we provide here are different kind of error models. Either, of course, you can also train for a specific kind of spike train in output. So if you want to reconstruct some specific signal, but in this case, since we are doing classification, we want to maximize the frequency of the neuron associated to the specific class. Yeah, so we can specify the training loop as usual with Torch. We can let the network train for a while. Yeah, and what we have here are the learning curves, usual that we have in deep learning. You can see the accuracy on training and testing, and we see that it goes down quite nicely. We can export the model for inference later, and we can also visualize the network output. And this probably clarifies also the kind of computation that we are doing. Right, so we have these inputs on the left that are changing through time, and on the right we have the output of the last layer. As you can see, we have, like for example, in the first row, we see that there are lots of spikes on the neurons associated with the correct class, and then towards the end of the input sequence, we have kind of a messy input, right? And then actually the network is not able to recognize the digit anymore, right? The important point here is that you can increase the kind of number of steps that you use to understand the class. So you see that you have multiple spikes through time. So you can increase the window that you're using to compute the spike frequency and then the class. But of course, you can also want maybe to minimize this window such that you can have minimum latency to the prediction, right? So you can just run the network for a minimum number of steps, and then you can use that to predict the class. And this somehow it's evident here in the sense that after a kind of initial delay that you have in the network, which is actually what is needed for the spikes to go from the input layer to the end of the network, then after that you already have kind of nice prediction of the digit. In the second case, it's you can see it's a little bit more messy, and this also clarifies the need for additional steps, right? So in the first kind of propagation of the input towards the network and then the output, you see that there are kind of spikes also in different classes. But then if you let the network run a little bit more, then you can see that then the frequency, it's actually maximized for the neuron associated to the true class.
Alessandro?
Yep.
But to me, it's not really messy. I mean, you have this transformation group type, and in between, it looks like a tree.
Yeah, yeah.
This would be even quite expected, right?
Yeah, yeah. It's
like this. Are you aware of any works in the direction of uncertain quantification with spiking?
Yeah, so we don't directly work on that in our group, but the kind of work that you can do usually in spike neural networks is work on ensemble models to quantify uncertainty. But yeah, I mean, we can of course discuss that. It's interesting direction for sure. Okay, yeah. So I at the end of the tutorial. So if you have questions, I'm here, or we can also catch up after the or during the coffee break. Thanks for the attention.